Volumes and surface area. In all the previous geometry lessons, we looked at shapes in 2 dimensions. Now we're going to step up to 3-dimensional figures. In 2D, we could talk about the area of shapes. In 3D, we will also talk about the volume of shapes. We'll start with the easiest of 3D shapes, the cube. Very special shape. And of course, a cube has 6 faces, 6 sides, and these are 6 congruent squares. It has 8 vertices and 12 edges. And it's true that at every edge, 2 faces meet in a perpendicular manner, and at every vertex, 3 edges meet mutually in a mutually perpendicular manner. So it's all right angles, all the meetings of edges and faces. A square has an edge length of s, then its volume is given by s cubed, s times s times s, or s cubed. And in fact, when we raise a number to the 3rd power, we call this cubing the number precisely because this is how we find the volume of a cube. So just the words squaring and cubing are actually geometrically grounded. They're actually connected to the shape of a square and the shape of a cube, even though we use these terms when we're in a non-geometric context. Each face on this cube is a square with side s, so each would have an area of s squared, and of course there are 6 sides, so the total surface area is 6s squared. Those are the 2 formulas for the cube, and those are both good ones to know. And again, don't just blindly memorize these. Actually think these through and understand why these are true, but these are good to know and good to be familiar with. The cube is the special case of a more general category known as rectangular solids. So the sides of a rectangular solid can be rectangles, but we still have the requirement that the faces meet at right angles at each edge, and 3 mutually perpendicular edges meet at each vertex. So there's still right angles everywhere, just now the lengths are different. So a rectangular solid, some people might just think of this as a box or something like that. The volume is the product of the 3 different edge lengths. So volume equals height times width times depth. The surface consists of 2 h times w faces, 2 h times d faces, and 2 w times d faces. So the total surface area is this. Again, these 2 formulas, the 2 formulas for a rectangular solid, it's very good to be familiar with these formulas, but again, do not blindly memorize them. Make sure you understand and can reproduce these on your own. In rectangular solids, we can consider 2 different kinds of diagonals. One kind, called a face diagonal, is the diagonal along only one face of the solid. So for example, on the front rectangle, we have this line AC, and of course we see legs of 3 and 4, so we know it's a 3, 4, 5 triangle. We could just use the Pythagorean theorem, so AC equals 5. And so that is just connecting across one face. It's still on the outside of the rectangular solid. The other kind, called a space diagonal, this actually goes to the inside of the solid and actually goes through the absolute center of the figure. So it passes through the interior from one vertex to an opposite vertex. So here, from A to D. And so A and D are not along any face. There's no single face that contains both A as a vertex and D as a vertex. They are opposites. So for this, we can use a 3D version of the Pythagorean theorem, where we just square the 3 individual leg lengths, and then that will equal the square of the space diagonal. So here, we're going to add up 9 plus 16 plus 25, so that adds up to 50. So the space diagonal AD equals the square root of 50, and of course 50 is 2 times 25, so we can write square root of 50 as square root of 25 times 2, and the square root of 25 simplifies to 5, so this is just 5 root 2. That was a whirlwind tour of simplifying radicals. If simplifying radicals is something that's not familiar to you, please watch the video on simplifying radicals, where this is discussed in detail. What is the length of the space diagonal of a cube of edge length s? Well, again, the 3D Pythagorean theorem, ab squared would be s squared plus s squared plus s squared, which is 3s squared. Take a square root of both sides, we get the space diagonal is square root of 3 times the edge length. And in fact, the test loves that little factoid, so that's a good one to know also. Here's a practice problem. Pause the video and then we'll talk about this. Okay, let's talk about this. We have the length of two edges and we also have the length of the space diagonal. So we don't know what that depth is, but we know that 4 squared plus 6 squared plus d squared equals 8 squared. So 4 squared 16 plus 6 squared 36, add those together, that's 52, equals d squared plus 64. D squared equals 12, so d equals square root of 12, or we can simplify that to 2 square root of 3. And again, if simplifying square roots is something new to you, please watch the video on simplifying square roots in the powers and roots section. That's where it's discussed in detail. So the depth is 2 root 3. Well, now we have the height, the width, and the depth, so we can just multiply those together. 4 times 6 is 24, times 2 is 48. We get 48 root 3, and that is the volume. Another 3D shape the test could expect you to know is the cylinder. A cylinder, when resting on one circular base, has a height of h. The radius of each circular base is r. Of course, a cylinder is a very common shape. Any can, for example, is a cylinder shape. The volume of this is pi r squared times h. And that's a really good formula to know. So basically, area of the base times the height. The total surface area of a cylinder is very interesting, and the test might ask about this also. Obviously, the top and the bottom are easy. Each is an area, it's a circle, so it has an area pi r squared. Think about the curved side, what is called the lateral surface of a cylinder. Think about the paper label on a metal can. If you were to take a razor blade and make a vertical slice and cut the label, then you could unroll it into a flat triangle. A flat rectangle. And so here's an example. We see the top and the bottom, and imagine that's the label of the can unrolled. So of course the height of that rectangle is the height of the can. And the top edge of that rectangle is what was fitting around the loop of the circle. It was fitting neatly around the loop of the circle. So of course that length is the circumference of the circle, 2 pi r. And so the height of the rectangle is h. The width is 2 pi r. And so the lateral area is just the product of those, 2 pi r times h. And then if we add two circles, pi r squared plus pi r squared, or 2 pi r squared, that's the total area. So again, this is good to know, but do not memorize this. Make sure you understand the argument. Might even help to cut the label off a can and visualize this yourself, so that you really understand where the surface area comes from. The only other 3D shape I will mention is the sphere. You don't need to memorize anything about this. You simply need to know what it is. If they ask you for any calculations, they'll give you the formula. Every point on the sphere is equidistant from the center, and the sphere is the only shape that is circular when viewed from every single direction. So no matter how you turn it around, the silhouette it has is always a circle. I'll say that the surface of the Earth is roughly a sphere. In fact, the Earth technically is a little wider at the equator, so it's not a perfect sphere, but it's roughly a sphere, and it's a way to think about it. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, a cylinder neatly encloses a sphere so that the curve of the cylinder touches the sphere in a circle at its widest, and the top and the bottom faces are tangent to the sphere. So in other words, wrapped around, the cylinder fits snugly around the circle, and in fact they're touching right around here, where the sphere is its widest, it's touching this. And then there's a point of tangency at the top and the bottom where the top of the can and the bottom of the can exactly touch the sphere. So if the volume of the sphere is 4 pi r cubed, what fraction of the cylinder does the sphere occupy? So first of all, the radius of the sphere and that of the cylinder must be the same. They both must have radius r. The height of the cylinder must be as tall as the sphere. So it's r from the bottom up to the midline, and then another r from the midline up to the top. So that's actually a height of 2r. The diameter of the sphere, another way to say that is that from this point at the top to this point at the bottom is a full diameter, and a diameter, of course, is 2r. So that's the height. The height is 2r. So volume of a cylinder is V equals pi r squared h, and for that h we're going to plug in 2r. So what we get is 2 pi r cubed. So that's the volume of the cylinder. So now we know the volume of the cylinder, we know the volume of the sphere, and we want to find the ratio. If we divide 4 pi r squared by 2 pi r squared, we divide 4 pi r cubed by 2 pi r cubed, then the pi r cubes will cancel, and we'll just be left with 4/3 over 2, or in other words, 4/3 times 1/2, and that simplifies to 2/3. So that's the answer. The sphere takes up 2/3 of the cylinder. And in fact, a cool historical fact, that diagram of a sphere inside a cylinder was the diagram that appeared on the tombstone of the great mathematician Archimedes. In summary, facts about the cube, its volume, its surface area, a rectangular solid, its volume and the surface area, and then the cylinder, its volume and surface area. For all of these, do not merely blindly memorize isolated factoids, but make sure you understand why these formulas are true.